You know, you see these perfect, glowing 3D models on a computer screen all the time, but have you ever stopped to think about how that digital dream becomes a physical object you can actually hold in your hand? How does every single curve, every hole, every surface get made exactly right, no matter where in the world it's built? Well, it's not magic. It's a language. And today, we're going to dive into this hidden language of engineering.
All right, so here's our roadmap. We're going to start with the big challenge, going from a perfect 3D model to a real part. Then we'll learn the language of precision that makes it all possible. We'll get into its core grammar, things called datums and tolerances, and finally, we'll see how it all comes together in the modern world on a digital drafting table.
So, our whole journey really begins with one fundamental problem. How do you bridge the gap between the perfect, clean world of a computer and the messy, imperfect reality of manufacturing? I mean, look at this. Inside a computer, everything is exact. This 3D model, probably made in a CAD program like NX, has surfaces that are flawless, dimensions that are perfectly defined. It really does exist in this state of theoretical perfection. And that is the multi-billion-dollar question, right? How do you communicate this idea of perfection to a machine or to a machinist who has to make a real thing, a thing that's subject to tiny vibrations, tool wear, even changes in temperature? How do you define what perfect enough actually means?
Well, the answer is a universal, standardized language. It's a system that lets an engineer in one country communicate their exact design intent to a manufacturer halfway across the world with absolutely zero ambiguity. And that language is called GD&T.
So what is it really? Think of GD&T as the official rule book for making stuff. It uses a whole set of standardized symbols to say exactly how much a real-world part is allowed to be different from its perfect digital design. You know, it's the difference between saying, make this about 10 millimeters, and saying, this must be between 9.9 and 10.1 millimeters, and there are no exceptions. Here's a great way to think about it, and I love this analogy. If the basic numbers, the dimensions on a drawing, are the words, then GD&T is the grammar. It's the sentence structure. It's what makes sure that everyone, everywhere, reads the instructions the exact same way. It's designed to remove all the guesswork.
Okay, so to build anything with precision, you need a starting point, right? A stable frame of reference. In the world of GD&T, that foundation is built on something called datums.
Okay, this is a super important distinction. Imagine a slightly warped wooden table. The physical, uneven top you can actually touch. That's the datum feature. It's real, it's imperfect. But to measure anything on it accurately, you'd probably lay a perfectly flat piece of glass on top of it. That glass represents the datum. It's the ideal, perfect plane that we measure everything from. We always measure from the ideal, not from the imperfect reality. And this just nails the concept. As GD&T expert Matt Durr puts it, one is something you can touch, the physical reality. The other is a theoretical representation, that perfect ideal we use for all our calculations and inspections. All right, here's a fun little piece of engineering trivia that shows you just how deep these standards go. You'll see datums on a drawing labeled A, B, C, D, but you will never see datums labeled I, O, or Q. Ever wonder why? Well, the reason is actually really simple and practical. It's a legacy rule, a holdover from the days of manual drafting. See, on old drawings, people often use the same physical stencils for the letter I and the number 1, and the same for O and 0. So to avoid any possible confusion, those letters were just banned from being used as datums. It's a rule that's just stuck around to this day. Okay, let's move on to the next key idea. If datums create the perfect starting point, tolerances are how we deal with the inevitable messiness and imperfection of the real world. The simple truth is, no machine can make a part perfectly. It's just not possible. A tolerance is how engineers define the acceptable range of that imperfection. It's like saying, hey, this hole doesn't have to be exactly 10 millimeters, but it absolutely must be somewhere between 9.9 and 10.1. It's basically the official engineering definition of good enough. So what about controlling the shape of just a single surface? A question that comes up a lot is why a control like flatness, which just makes sure a surface is, well, flat, doesn't need to be referenced to a datum. And the answer is that flatness is an internal check. You're not comparing that surface to anything else on the part. You're just asking, are all the points on this one surface within a certain tiny range of each other? It's an intrinsic property. It's checking itself against itself. So you just don't need an external reference or a datum.
So, we've got our language and its grammar. Now let's see how an engineer actually writes with it using modern computer-aided design or CAD software.
This right here is the annotation toolbar in a program like Siemens NX. You can think of this as the engineer's palette. Each one of these buttons represents a specific GD&T symbol. They can just grab a datum feature symbol, define what's called a feature control frame to apply a tolerance, or even add instructions for things like weld symbols and surface finish. It's all right there.
And the workflow is really logical and powerful. An engineer just selects the symbol they need. A little dialog box pops up where they define all the specific rules and values. They then click on the geometry of the 3D model to link that rule directly to a feature. And finally, they place the resulting symbol on the 2D drawing. Simple as that.
Now, here's the magic of modern systems. All of this rich data, the tolerances, the datums, all the notes, it's called Product and Manufacturing Information, or PMI. This isn't just dead text on a drawing anymore. It's intelligent data that's literally linked to the 3D model. So when a 2D drawing view is created, all this PMI can be automatically pulled in, which makes sure the model and the drawing are always perfectly in sync. So why does any of this matter? What's the big deal? Well, because this standardized language, embedded as intelligent PMI in a digital file, is what allows our incredibly complex global supply chain to even function. It's how a designer in Germany, a factory in China, and an assembly plant in Mexico can all work from the exact same plan and build a product that fits together perfectly, every single time.
So the next time you happen to see one of these seemingly cryptic blueprints, don't just see a bunch of lines and numbers. See it for what it really is, a precise story, told in a universal language that describes a journey from a perfect idea into a physical reality. What story will its symbols tell you?